Hello friends, welcome to CEC Live Lectures. Dear friends, today in this session we are going to talk on our series on natural products and spectroscopy. We have done ample of lectures under this series. Today we are going to talk on terpenoids specifically. Dear friends, in the first half we would be discussing on what terpenoids are, as well as we would be discussing on the classifications of terpenoids. In the second half we would be discussing on the structure determination, and for the discussion we have with us in our studios Dr. Sushila Singhal. Dr. Sushila Singhal is Assistant Professor in Department of Chemistry, Deshbandhu College, University of Delhi. Friends, if you wish to ask questions from Dr. Sushila Singhal on today's topic, then do call us through our toll-free number. Our toll-free number is 1800-110-430. I repeat, our number is 1800-110-430. Now, I would like to welcome our guest, Dr. Sushila Singhal, and would request her to continue. Hello, ma'am. Welcome to the lecture.
Thank you, Geetika ji. Good day, viewers. Today, in the series of natural products and spectroscopy, we are starting a new topic, terpenoids. These terpenoids are generally derived from the plants, and in plants also, these are derived from the herbs and some trees and some fruits also. So these terpenoids are the hydrocarbons basically, which have some aroma and which have some smell. These are of great importance in the medicinal properties, since these are applicable to some drugs and some syrups which are of some antibacterial and antimicrobial importance. So we are starting in the first module, we will be discussing the terpenoids in introduction. Then, since we know that these are the hydrocarbons and some oxygenated hydrocarbons are also termed as the terpenes, so we will discuss about the structure of these terpenes, which basically includes two rules. One is the Isoprene Rule and one is the special Isoprene Rule. Then we will discuss the GemDialkyl Rule. Further, we will discuss about some general properties of terpenoids. Then we will discuss the classification of terpenoids, how we will isolate these terpenoids from the natural sources, and then we will study that how we will separate out these terpenoids from the essential oils. In the second module, we will be discussing the general methods of structure determination of terpenoids, which includes the many steps. One is the analytical methods, then the synthetic methods, then physical methods, some knowledge of a molecular rearrangement, and finally these structures will be confirmed by their synthesis in the laboratory. So in the first the introduction of the terpenes, that these terpenes which are derived from the essential oils present in the herbs and in the trees, these terpene basically the term this terpene was employed to describe a mixture of isomeric hydrocarbons of the molecular formula C10H16 occurring in the turpentine and the many essential oils which are obtained from the sap and some tissues of certain plants and trees. These terpenes and terpenoids both are the primary constituents of the essential oils of many types of plants and flowers. Essential oils are used widely as fragrances in perfumery and in medicine and some alternative medicines such as the aromatherapy. So basically these terpenes, because of their smell, they are very important in the aromatherapy technique of the medicines. Synthetic variations and derivatives of the natural terpenes and terpenoids also greatly expand the variety of aromas used in perfumery and flavors used in the food additives also. You might have heard about the vitamin A. It is also a kind of terpenoid. If we talk about the definition of the terpenoid, it includes hydrocarbons of the plant origin of the general formula C5H8 with the multiple of N, as well as their oxygenated, hydrogenated and the dehydrogenated derivatives. The term terpene is generally rejected since the suffix "ene", as you are hearing, we are saying that this is terpene. So the last three words, that is the "ene", it signifies the unsaturated hydrocarbons, and the name terpene is inappropriate to include the compounds such as alcohol, aldehydes and ketones etc., since we are saying that some oxygenative derivatives of hydrocarbons are also termed as the terpenes. Now we will term these terpenes as terpenoids. Now, as terpenoids are composed of isoprene units, these are sometimes called as isoprenoids also. The fragrances of many plants arise from the volatile C10 or the C15 terpenes. It means these terpenes, they contains the carbon number from 1 to 10, or they may contain carbon up to 15 and more than that also. These and their oxygenative derivatives, they occur as a component of the essential oils, some of which are used as perfumes. Important monoterpenoids are mycene, which is derived from the oil of bay, geraniol, which is derived from the rose oil, limonene, which is derived from the lemon oil, and menthol, which is derived from the peppermint oil. Among the sesquiterpenoids, farnesol is widely distributed, but it is present in essential oils in small amounts only. Diterpenes are usually found in the substituents of the resins and the balsams. The two resin acids, one is the abatic and one is the sapiatic, are the best known tricyclic diterpenes. Vitamin A1 and vitamin A2 and their aldehydes, which are also called as retinins, are important monocyclic derivatives of the diterpenes. The simplest unit of terpenoids is isoprene. Two or the more isoprene molecules take part in the synthesis of isoprenoids or the terpenoids. Examples of isoprenoids are various terpenes, some fat soluble vitamins, and the bile salts, etc. Here we have shown you the structure of its monomer. We can say that this isoprene is a monomer of this polymeric terpene or the terpenoid moiety. So here we have shown you the structure of terpene. It contains 5 carbon, and this is the simplest monomeric unit of the terpene. And these terpenes are hydrocarbons, which are non-saponifiable lipids, which are found in the plants. In general, these hydrocarbons and their oxygenative derivatives have lesser than 40 carbon atoms. The simplest terpenes are called as the monoterpenes, which conform to the formula C10H16, which is equivalent to 2 isoprene unit. It means that in the simplest one terpene, which is the monoterpene, at least 2 isoprene units must be there. Nearly all the terpenoids are made up of varying number of repetitive units of isoprene, and which are based on the Isoprene rule. Now we will discuss about the Isoprene rule, what it is. In 1887, a scientist Wallich, he initiated the famous Isoprene rule, which may be stated as follows: the skeleton structures of all naturally occurring terpenoids are built up of isoprene units. So it is the base of all the terpenoids. From the above rule, it follows that the divisibility into the isoprene units is regarded as a necessary conditions to be satisfied by every naturally occurring terpenoids. It means that if we decompose any hydrocarbon of the terpenoid, it will convert into some isoprene units. The Isoprene rule has been deduced from the following facts: that the empirical formula of almost all the naturally occurring terpenoids is C5H8, which is the isoprene itself, and the thermal decomposition of almost all the terpenoids will give the isoprene as one of the products. For example, if we talk about the rubber, which is a polyterpenoid, when it is destructive distillation is worked on the rubber, it yields the isoprene as one of the decomposition products. So this rubber, after decomposition into the monomeric state, it finally will give us the isoprene. So this Isoprene rule has been confirmed by the fact that under special experimental conditions, isoprene undergoes polymerization to yield the various terpenoids. For example, isoprene, when it is heated to 280 degrees centigrade, it gets dimerized to yield a widely distributed terpenoid called the dipentene. So dipentene is a monoterpenoid which contains 2 isoprene units together. Here we have shown you this systematic dimerization of this isoprene unit. When it is heated, it will convert into the C10H16, which is called as a dipentene, and it is a terpenoid. Isoprene may be polymerized to give a rubber-like product, which is a polyterpenoid. If we take the n number may be more than 40. When they polymerizes together, they forms a polyterpenoid, which is called as the rubber. Then comes a special isoprene rule. From the isoprene rule, we have stated that all the terpenoids contain the isoprene units. Now the question comes that these isoprene units, how they are arranged together to give a terpenoid. So for the arrangement of these isoprene units all together, there is a special isoprene rule which will define its special type of arrangement, which is known as the special isoprene rule. And this special isoprene rule, it is basically proposed by a scientist in Gold in the 1925, who shows that how the isoprene unit in a terpenoid molecules are linked together. For this purpose, the branched end of the isoprene unit is considered as the head, and the other end of the isoprene unit is termed as the tail. Now, according to this special isoprene rule, all the isoprene units in the terpenoids are linked in a head to tail fashion. So this arrangement, which is the head to tail fashion, is termed as a special isoprene rule. Thus, the basic skeleton of a monoterpenoid, which contains the at least the two isoprene units according to the special isoprene rule, will be shown like this. We have shown you in the structure here. This is the first isoprene unit, and this one is the second isoprene unit, and this branching end of the isoprene is termed as the head, and this unbranched part of this isoprene is the tail part. And in the second unit, again this branching part of isoprene is the head, and the unbranched part is the tail. So the arrangement is head to tail, again head to tail. This kind of arrangement, this kind of special arrangement in the 3D structure of the terpene system is basically based on this special isoprene rule. Similarly, if we talk about the sesquiterpenoids, which contains the 3 isoprene units, the skeleton will be like this. Again, you can see here it is again a head to tail fashion. This is the head part, this is the tail, again the head, tail. So here again the special arrangement of isoprene units in the sesquiterpenoid, it is according to the special isoprene rule. Now, it should be noted, however, that this rule, which has proved very useful, can only be used as a guiding principle and not as a fixed rule. Therefore, there are some departures and violations of this rule in many compounds. For example, certain terpenoids are known whose carbon content is not a multiple of 5. For example, krypton is a terpenoid, a naturally occurring ketonic terpenoid. It contains a 9 carbon atom, and therefore it cannot be divided into the 2 isoprene rule. So here it is not following the isoprene rule as well as the special isoprene rule. Certain terpenoids are known whose carbon content is a multiple of 5 but cannot be divided into the 2 isoprene units. So it is also a departure from the isoprene rule. Certain terpenoids are also known in which the special isoprene rule is only violated. For example, levendulol is composed of the 2 isoprene units of isoprene with the unusual linkage of tail to tail but not head to tail. So there is a deviation from head to tail arrangement. So it is again a violation of the special isoprene rule. Also, the carotenoids, which are again the unsaturated hydrocarbons, are joined tail to tail at their centers. Here we have shown you the 2 examples. One is the krypton. Here again there is a tail to tail arrangement, and in the levendulol, this is the branching part, which is the head, and this is the tail part of this isoprene unit, and this is the another isoprene unit which is joined in a tail to tail fashion, tail to tail pattern. So this is again a departure from the special isoprene rule. Then comes the one more important rule, that is the GemDialkyl Rule. If the 2 functional groups, they are present on the adjacent carbons, they are generally termed as the geminal carbons, geminal functional groups. So this rule is based on that geminal pattern of hydrocarbon arrangement. When the 2 alkyl groups are attached to the same carbon atom, it is called the GemDialkyl group. and when they are present at the adjacent carbons, they are termed as the vicinal dialkyl rule. So here in case of terpenoids, it is generally the geminal dialkyl groups. The presence of GemDialkyl group affects the stability of terpenoids. This was observed by the Ingold, who summarized his results in the form of empirical rule called the GemDialkyl rule, which may be stated in words as follows. The GemDialkyl group tends to render the cyclohexane ring unstable, whereas it stabilizes the 3, 4 and the 5 membered ring. So here the stability of terpenoid is generally affected by this, the GemDialkyl groups. The GemDialkyl group is helpful in two ways. This rule limits the number of possible structures of terpenoids. For example, the monoterpenoid open chain would give rise to only one possibility for a monocyclic monoterpenoid. That is, the paracymene structure, which is shown as follows. Here we have shown you the structure of paracymene. You can see here. Here this is the dialkyl part, and this is the one isoprene unit, and this is the second isoprene unit. So if we decompose, if we divide this paracymene structure into the two half, we will get here the two isoprene units which contains the GemDialkyl groups. The most natural monocyclic monoterpenoids are generally the derivatives of this simple structure, that is the paracymene. This rule helps to find the carbon skeleton of cyclic terpenoids also. Thus, the 6-membered terpenoid should contain the GemDimethyl group outside the ring, whereas the bicyclic terpenoids should contain the GemDimethyl group on the smaller ring, that is the cyclopropane and the cyclobutane ring, to render them sufficiently stable to be capable of occurrence in nature. For instance, the closure of C10 open chain would give rise to 3 possible structures. Actually, all the 3 are shown here, where we are having the C10 structures. So there are 3 possibilities that the GemDialkyl parts are within the ring. So they will stabilize these terpenoids. Then comes the general properties of terpenoids. Terpenoids are basically colorless liquids which are generally present in the essential oils of plants, and these are lighter than water and boil between 150 to 180 degrees centigrade. A few are solids which are lighter than water, volatile in steam, usually having the high refractive index, and are insoluble in water but soluble in the organic solvents. Many of these terpenoids are optically active. They are unsaturated compounds which are open chain or cyclic with one or more carbon atom rings having one or more double bonds. Since they are unsaturated compounds, consequently these terpenoids undergoes addition reactions as double bonds are present, as these are unsaturated compounds. So these will undergo the addition reactions with the hydrogen, with the halogen acids, etc., and some of them can form the hydrates also. They are also form characteristics addition products with the with the NO2, NOCl and the NOBr. So they can form these kind of complexes also, and these additional products are found to be useful in the identification of the terpenoids. A number of additional products have the antiseptic properties. They undergo polymerization, also the dehydrogenation in the ring. As they are olefinic bonds, as they are the double bond, they are unsaturated, they are very easily oxidized nearly by all the oxidizing agents. A number of terpenoids are labile and hence readily isomerizes in the presence of acids into the more stable forms. On thermal decomposition, most of the terpenoids, they yield the isoprene as one of the products. So it states that all the terpenoids, they contains the isoprene unit as the monomeric unit. Then comes the classification of terpenoids, that how these hydrocarbons has been classified. Terpenoids are generally classified on the basis of number of isoprene units present in them. Natural terpenoid hydrocarbons have the molecular formula C5H8 with the number N, where N is the basis for the classification. If this N is the 2, it means that it contains the 2 isoprene units, then it will be termed as a monoterpenoids and molecular formula will be C10H16. And if it is the 3, that is the 3 isoprene units, when these are joined together, then the molecular formula will become C15H24 and it will be classified as sesquiterpenoids. Now if it contains the 4 isoprene unit, the molecular formula will be C20H32 and these will be classified as the diterpenes. If it contains the 5 isoprene units, it will be termed as a sesterterpenoids and the molecular structure will be the C25H40. If it contains the 6 isoprene units, the molecular formula will be C30H48 and these will be classified as the triterpenoids. If it contains 8 isoprene units with the molecular formula C40H64, then these are termed as the tetraterpenoids. And if it contains this carbon, this N number, more than 40 isoprene units if are present in a particular hydrocarbon, then these will be termed as the polyterpenoids. The sesquiterpenoids have been discovered recently and so far only very few are known. In addition to the hydrocarbon, in each class, oxygenated compounds like alcohols, aldehydes, ketones are also known which occur in nature. And each class of these terpenoids have been further subdivided into subclasses according to the number of rings present in the molecule. They may do not have any ring, so if they are open chain structure, they will be classified as acyclic terpenoids. If they contain one ring in the molecule, they will be classified as monocyclic terpenoids. If they contain 2 rings in the molecule, they will be termed as a bicyclic terpenoid. If it contains 3 rings in the molecule, then it will be termed as a tricyclic terpenoids, and with the 4 rings it will be termed as a tetracyclic terpenoids. So on the basis of number of rings, we can subclassify these monoterpenoids and sesquiterpenoids into different classes. Then comes the isolation of terpenoids, at how we will isolate these terpenoids from the natural sources. Now, due to their wide occurrence in nature, all the terpenoids could not be isolated and separated by a general method. So, we have to use very different kind of strategies, different kind of methods for the different terpenoids. However, the mono and the sesquiterpenoids have a common source, that is the essential oils, and therefore their isolation has been generalized. This is carried out in the 2 steps as follows. First, we will isolate the essential oils from the natural sources. Then there will be a separation of terpenoids from these essential oils. So first we will discuss about the isolation of essential oils. As the plants having the essential oils generally possess maximum concentration at some particular time. For example, jasmine at sunset only, it becomes desirable to take the plant part having the essential oils at this particular time. In general, the several methods based on the different principles have been developed for the extraction of oils from these plants. The first method is the expression method. In this method, the plant material is first cut into the smaller pieces. Then these are crushed to get the juice, which is screened to remove the larger particles. After screening, the juice is centrifuged into the centrifugal machine in a high speed rate, when one half of the oil is extracted and the rest half of the essential oil remains with the residue. Now from this residue, inferior quality of the oil is obtained by distillation. Expression method is generally used to extract citrus, lemon and the grass oils. This method is not used these days. Then comes the steam distillation method. This method is one most widely used method. In this method, the plant materials are macerated, are again crushed and then steam distilled to get the essential oils into the distillate. The distillate is then extracted by using the pure organic volatile solvents like light petroleum, and the solvent is then removed by distillation under reduced pressure. One should employ steam distillation method carefully because it suffers from the following demerits. Some essential oils undergoes decomposition during the steam distillation, and some constituents of the essential oils, for example the esters, which are responsible for the odor and the fragrance of the oil, may undergo decomposition, resulting into a perfume of inferior quality. So this distillation should be done very carefully. Then comes the third method, that is the extraction by means of the volatile solvents. This method is generally used for such plants which yield an oil or which gives very low quantities of oil on steam distillation due to the decomposition of the essential oils. In such cases, the plant material is directly treated with the light petrol at 50 degrees centigrade. Under these conditions, the oil is taken up by the solvent along with the soluble coloring materials. The essential oils from this extract are separated by removing the solvent by distillation under reduced pressure. This method is widely used in the perfume industry. Then the another method is the adsorption method, which is generally adsorbed on the fat content. So it is also called as the enfleurage method. This method is basically employed in the France. By this method, the yield of the essential oil is generally higher. This method is used to extract a large number of essential oil like the rose oil and the jasmine oil. In this method, the fat taken in the glass plate is warmed to about 50 degrees centigrade. Then the surface of the fat is covered with the flower petals from where we have to extract the essential oil, and then it is allowed to be kept as such for several days until it becomes saturated with the essential oils. Until this fat is fully saturated with the essential oil, then the old petals are replaced by the fresh petals, and this process is repeated till we get the maximum quantity of the maximum yield of the essential oils. After removing the petals, the fat is then digested with the ethyl alcohol. When the essential oils present in the fat are dissolved in the ethyl alcohol, some quantity of fat is also dissolved in the alcohol. This can be removed by cooling the alcohol extract to 20 degrees centigrade when the fat separates out. The solvent is distilled off to get the essential oils. The essential oil so obtained contains a large number of terpenoids, and these are then separated by the fractional distillation methods. The terpenoid hydrocarbons distills first, and these are followed by the oxygenated derivatives of the terpenoids. Distillation of the residue under reduced pressure gives the sesquiterpenoids, and these are separated by the fractional distillation. More recently, various forms of chromatography have been used for the isolation and separation of the terpenoids. Adsorption chromatography using alumina or the silica gel as adsorbent have provided the most important method for the isolation and separation of terpenoids, particularly the triterpenoids. Additionally, the fat has been replaced by the coconut charcoal due to its greater stability and the higher adsorptive capacity. After keeping the coconut charcoal in contact with the petals for a number of days, the charcoal is submitted to steam to get the essential oils. This method is superior to the method which we have discussed earlier, which is the enfleurage method. Then comes the separation of terpenoids from the essential oils. After isolation of the essential oils, then we will separate the terpenoids from these essential oils. So again there are various methods. One is the chemical method. When the essential oils containing the terpenoid hydrocarbons are treated with nitrosyl chloride in chloroform, the crystalline adduct of hydrocarbons having the sharp melting points are obtained. These are then separated and decomposed into their corresponding hydrocarbons. When essential oils containing the alcohols are treated with the phthalic anhydride to form the diesters, the primary alcohols react with the phthalic anhydride readily, secondary alcohol less readily, and the tertiary alcohol do not react at all. After extracting with the sodium bicarbonate, diesters are decomposed by the alkali to the parent terpenoid alcohol. Here we have shown you the reaction in which we have taken here the phthalic anhydride. When it reacts with the alcohol, with the terpenoid, it first forms the diesters of these phthalic anhydride, which on reaction with the potassium hydroxide, then it will convert into the phthalic acid and with the 2 alcohol moieties. So here we can get the terpenoid from this method. Then the terpenoid aldehydes and ketones are again separated from the essential oils by forming their adducts with the common carbonyl reagents like the sodium bisulfite, like 2,4-dinitrophenylhydrazine, phenylhydrazine and the semicarbazide, etc. After separation, they are then decomposed to regenerate the terpenoids, aldehydes and the ketones. So now in the second module, we will discuss about some reactions of these separation of terpenoids from the essential oils. Thank you.
With this note, thank you ma'am, thank you so very much. Dear friends, we learned a lot about terpenoids in this session. We would be discussing on structure determination in the next session. You are requested to be with us. We are back after a short break. Thank you. Hello friends, welcome back to this session. Friends, in this session we are going to discuss on structure determination. In the first half we discussed what terpenoids are, whereas as we promised that we are going to discuss on the structure determination. So here we are, and for the discussion we have with us in our studios Dr. Sushila Singhal. Friends, if you wish to ask questions on the topic from Dr. Singhal, do call us through our toll-free number. Our number is 1800-110-430. Now I would like to welcome our guest Dr. Sushila Singhal once again and would request her to explain us in detail about the structure determination of terpenoids. Hello ma'am, welcome to the lecture.
Thank you, Amriti. Welcome back, students. After discussing the separation of terpenoids from the essential oils, after discussing the chemical method, the second method is a physical method which contains a fractional distillation method. The various terpenoids which are present in the essential oils, since they have the mixture of terpenoids, so we have to separate them out with the fractional distillation method. The terpenoids, which are basically the hydrocarbons, they will distill out first, and then the oxygenative hydrocarbons, the oxygenative terpenoids will distill off after the distillation of the first hydrocarbons. The distillation of the residues under the reduced pressure yields the sesquiterpenoids, and these are separated by again the fractional distillation. On an industrial scale, the specially designed stills are employed, and an efficient condensing system is necessary to minimize loss of more volatile hydrocarbons. Since many terpenes are sensitive to heat and atmospheric oxygen, so the fractional distillation many times has to be carried out under reduced pressure and in the presence of the inert gas. Then comes the physical method, which is basically the chromatography. Chromatography is a method where we separate these terpenoids with some different colors when these terpenoids are absorbed on some adsorbents, then there is a separation of these terpenoids which can be identified with the coloring method. More recently, the chromatography in its various forms has been widely used both for the isolation as well as for the separation of the terpenoids. In adsorption chromatography, the essential oil is made to flow through a particular adsorbent when the different types of terpenoids are adsorbed at different places on the adsorbent to form the different chromatograms. Then the various chromatograms are eluted by the different solvent systems to get the different eluates. Each eluate is having the terpenoid of a single group. Each eluate is then subjected separately to adsorption chromatography when different bands due to the various terpenoids present in the eluate are obtained, which are then eluted to yield the different terpenoid. Then comes a general method for the structure determination of terpenoids. The fundamental research is done by Wallach, Bayer, Perkins, Semler, Simonson, Ruchika. These scientists, they worked on the structure determination of terpenoids, and they have defined some fundamental methods which are of great importance in elucidating the complicated structures of these terpenoids, which are the hydrocarbons and the oxygenated derivatives of the hydrocarbons. All the methods used for these have been grouped into some classes, into the 4 classes. One is the analytical method, one is a synthetical method, then comes a physical method, then knowledge of a molecular rearrangement. And then these 4 methods will be confirmed finally by the synthetic methods which are done in the laboratory. So we will discuss all these methods in detail. First comes the analytical methods. These includes the following methods. The first one is the molecular formula, that how we will design the molecular formula of a product which we have derived from the natural source. So we have to do some qualitative and quantitative estimation of the carbon and the hydrogens present in the hydrocarbons. Since we are saying that these are the hydrocarbons as well as the oxygenative derivatives, so we have to do the carbon, hydrogen and the oxygen estimation, the quantitative as well as a qualitative estimation of these elements, and after designing the empirical formula of that product, we will then design the molecular formula, which is also confirmed by means of the mass spectrometry. If the terpenoid is optically active, its specific optical rotation is also measured. Sometimes the optical rotation may be used to make distinction between the structures, as in the limonene and the carbone, since these are the two optical isomers. Then the other physical constants like melting point, boiling point, specific rotation, etc. are also determined for the terpenoids. Then comes the, after discussing the molecular formula, then comes the nature of the oxygen atom present. If the oxygen is present in the terpenoid, its functional nature is ascertained by the usual methods. The terpenoids generally contain the hydroxy, aldehyde, keto and the carboxylic groups. Other oxygenic functional groups are OCH3, that is the ether, CONH2, that is the amide linkage, NO2, nitro group, etc. have been reported in some terpenoids. The various groups are detected in terpenoids by the following methods. The hydroxy group can be detected by the formation of crystalline acetates with the acetic anhydride and benzoates with the 3,5-dinitrobenzoyl chloride. As we do the systematic analysis of any organic compound, same here we have to do a systematic analysis of the natural products of the terpenoids also. So first we will do the hydroxy group detection. For that we have to treat this terpenoid with the acetic anhydride. Here you can see in the reaction that we have taken here the oxygenative derivative of the terpenoid, and when we will treat it with the acetic anhydride, these crystalline substituted products, which are basically the acetates, these acetates are formed. Here again we have taken one more oxygenative derivative of terpenoid. When it is treated with the dinitrobenzoyl chloride, here it forms a 3,5-dinitrobenzoate. So by formation of these crystalline substitutes, we can say about the presence of the hydroxy group present in the given terpenoid. These terpenoids can also react with the phenyl isocyanate. When these are treated with the phenyl isocyanate reagent, they sometimes forms the substituted urethane. These also gives a kind of information that the hydroxy group is present in that particular terpenoid. Further information about the nature of the hydroxy group can be revealed by the rate of esterification. For example, the primary alcohols undergoes esterification more readily than the secondary and the tertiary alcohols. Thus, the alpha terpineol, which is a tertiary alcohol, is slowly esterified. Now, if the terpenoid, they form some additional products with the bisulfite derivatives, with the oxime and with the phenyl hydrazone, this shows that the terpenoid contains a ketonic group or it contains a carboxylic acid group. Here we have shown you these addition reactions of the presence of a carbonyl group present in a terpenoid. If this kind of linkage, if this kind of carbonyl group is present in the terpenoid, it can react with the sodium bisulfite, forming a addition product which is a sodium bisulfite derivative. It is a white crystalline compound. When this carbonyl moiety is present in the terpenoid, it can also form the addition product with the hydroxylamine. When hydroxylamine is treated with this kind of moiety, then generally forms the addition product which is termed as the oxime. These are again the white crystalline structures. By the formation of these kind of addition product, we can say that the carboxyl group is present in the given terpenoid. If this contains the carboxyl group, it can also react with the phenyl hydrazine. When it reacts with the phenyl hydrazine, then it forms the additional product phenyl hydrazone. So these kind of additional products can be formed if the carbonyl moiety is present in the given terpenoid. The carbonyl group may be present either in the form of aldehyde or it can be present in the form of ketonic group. This can be ascertained by the oxidation methods. The aldehyde on oxidation yields the monocarboxylic acid without the loss of the carbon atom. Whereas if the carbonyl group is a ketone, then on oxidation it will yield a mixture of lesser number of carbon atoms. Here you can see that if the aldehyde group is present in the terpenoid, it will oxidize to give a carboxylic acid which is a monocarboxylic acid with the same number of carbon atom. Here you can see that here again the along with this alkyl group we are having the one C1 in the terpenoid, and here again we are along with the alkyl group we are having the carbon number 1. If we have the ketonic moiety in the terpenoid and if undergoes oxidation, then we will get a mixture of these monocarboxylic acid, and here you can see that in these mixtures we are having the carbon lesser than the reactant which is oxidized. Terpenoids, if they contains the CH2CO group, they exhibits the special properties. This CH2CO group is basically the methyl ketones. Such terpenoids, they forms the oximes with the nitrous acid liberated by the action of hydrochloric acid on the isoamyl nitrate and the benzylidene derivative with the benzaldehyde in the presence of the alkali. Here we have shown you these two reactions in which if this group CH2CO group is present in the terpenoid, then it will react with this reagent in the which is derived from the amyl alcohol in the acidic medium, and they will form a oxime addition product. And if we again we are having this kind of moiety in the structure, it can also react with the benzaldehyde to give the benzylidene derivative. If these kind of derivatives are obtained by the reaction on these reagents, then we can say that it contains this CH2CO group in that structure. If this CH2CO group is present in the ring, the terpenoid on oxidation will yield a dicarboxylic acid without any loss of the carbon atom. For example, if we are having this moiety, if it undergoes the oxidation, then here both of these CH2 as well as the carbonyl group both will oxidize to give a carboxylic acid moieties without the loss of any carbon. This will again oxidize into a carboxylic acid, and the CO will oxidize into the carboxylic acid group. If we talk about the camphor, camphor is again a hydrocarbon, again a terpenoid which contains a ketonic moiety. It undergoes oxidation with a concentrated nitric acid. It yields a dicarboxylic acid. Here you can see that we are on oxidation, it will break from this linkage, and we will get here the dicarboxylic derivative of this camphor, which is termed as a camphoric acid. If the terpenoid, if it contains a COCH3 group, that is a methyl ketone, it can be detected by the haloform reaction. For example, if we are having this methyl ketone in the terpenoid, it can react with bromine in the presence of sodium hydroxide. Here it will form the salt of sodium and a bromoform will be formed, and by the color of this bromoform we can detect that it is undergoing the haloform reaction, and we will say that the methyl ketone group is present in that terpenoid. On oxidation, such terpenoids also forms acetic acids. For example, this methyl ketone, if it is present in the terpenoid, if it undergoes oxidation, it will give the acetic acid. If a terpenoid is soluble in ammonia and gives the effervescence with the sodium bicarbonate, then these facts reveal that the terpenoid contains a carboxylic group. As all of you know that the reaction with the sodium bicarbonate will give some effervescence, which are basically due to the ease of the carbon dioxide, so it may contain the carboxylic acid group. Number of carboxylic acid group is then estimated by the titration against a standard alkali. Sometimes it becomes essential to ascertain whether the carboxylic group is attached to a primary, secondary or a tertiary carbon. This is generally done from the determination of rate of esterification of the acid, which is generally in the following order, that primary will be esterified more easily than secondary and then tertiary. Tertiary carboxylic groups are very difficult to be esterified, and acids with such groups evolve the carbon monoxide with concentrated sulfuric acid. Also, such acids do not form halogen substituted derivatives, which are characteristics of acids having the alpha hydrogen atoms. Then comes the unsaturations, whether these hydrocarbons they contains a double bond or how many number of double bonds are present in them. For that there is a unsaturation test. The presence and the number of these olefinic double bonds in the terpenoids have been ascertained by the formation of addition products with various reagents like halogens, halogen acids, peracids and the nitrosyl chloride, which is also termed as a Tilden reagent. When a terpenoid possessing the olefinic linkage is hydrogenated in the presence of a catalyst, an addition compound called hydro compound is formed. From the number of hydrogen consumed, the extent of unsaturation in a terpenoid can be calculated. For example, the catalytic reduction of cadonine, it yields a tetrahydrocadonine, indicating that cadonine contains a 2 double bond. If it contains 1 double bond, then it might have consumed only the 1 H2, so it could have the dihydrocadonine. Now, since it yields the tetrahydro derivative, so we can say that there are presence of 2 double bonds in the cadonine terpenoid. With halogens, these terpenoids containing the olefinic linkage, they again forms addition compounds. The measurement of the amount of halogen used, it gives the amount of unsaturation. For example, if we do the bromination on any terpenoid which contains the olefinic double bond, then it will give the dihalo derivative of that terpenoid if it contains the 1 double bonds. Baer and the Villiger, these are the two scientists who employed the method of exhaustive methylation to ascertain the nature of carbon framework present in the terpenoid molecule. With the halogen acids like HCl or the HBr, the terpenoids they yield the addition compounds which can be characterized very easily. These addition compounds also often serves for the identification of terpenoids. In order to carry out the halogenation, the terpenoid is dissolved in a suitable solvent. and then the dry hydrogen acid gas is passed into it. For example, if we take the limonene, a terpenoid, with the hydrochloric acid, it yields a crystalline dihydrochloride, indicating that the limonene, it contains the two double bonds. You can see in the reaction, we have taken here the limonene. When it is reacted with the hydrochloric acid, it consumes the two molecules of hydrochloric acids. It forms a dihydrochloride, so it contains the two double bonds. And these addition of halogen acids, the addition of bromine, they generally takes place according to the Markovnikov rule. Now the question comes that what is this Markovnikov rule? So Markovnikov rule is a rule when an unsymmetrical reagent is added to unsymmetrical alkene, to the unsymmetrical double bond, then the negative part of that reagent will go to that carbon atom which contains a lesser number of hydrogen atom. So the addition of this halogen acid, it is according to this Markovnikov rule. Then comes the unsaturation, which gives the addition products with the nitrosyl chlorides. When the terpenoids containing the olefinic double bonds, they form the addition compounds which are crystalline products having the sharp melting points and may be used for the identification and separation of the terpenoids. Here again we have taken a reaction in which we have added the nitrosyl chloride, the Tilden reagent, to the carbon-carbon double bond, and we will get here the addition product, which is again a crystalline addition product. The addition of this nitrosyl chloride, that is a Tilden reagent, gives the idea about the nature of the carbon atom having the double bonds in the terpenoids. For example, if the two carbon atoms joined by an olefinic linkage are tertiary in nature, then a blue colored nitrosochloride is obtained. On the other hand, if one of the carbon atom joined to the double bond is tertiary while the other is secondary, a colorless nitrosyl chloride is obtained. So here the nature of linkage of the double bond can be ascertained by the reaction with the Tilden reagent. Here you can see in the reaction, when this carbon-carbon double bond, when these both the carbon are tertiary in nature, then the addition, after addition of this NOCl, nitrosyl chloride, the addition product which we are getting will be the blue colored product. And when this one of the carbon of the olefinic linkage is tertiary and the second carbon of the olefinic linkage is secondary, here you can see that this is the hydrogen atom, so this carbon is secondary in nature. When there is this difference of the carbon nature, then the addition of nitrosyl chloride will result into the addition product, which is a colorless product. So by the distinction of the color, we can ascertain the linkage of the carbon-carbon double bond, that whether it is present in a tertiary form or it is in a secondary form. Again, this nitrosyl chloride, the addition of this Tilden reagent is basically takes place according to the Markovnikov rule. Then comes the per acid addition. Per acids can also be used to determine the amount of unsaturation in a terpenoid molecule. With per acids, terpenoids containing the olefinic double bonds, they forms the epoxides. Here you can see in the reaction, when this unsaturation is present in the terpenoid and when it is reacted with the per acid contains one oxygen more than the acid, then this oxygen will be absorbed by this olefinic linkage and it will form the epoxide, which is a cyclic ether. A known amount of terpenoid is treated with an excess of per acid, that is a perphthalic acid in some cases, and then the unused amount of the acid is determined volumetrically. From the amount of per acids used, the number of olefinic double bonds can be determined quantitatively. In order to detect the presence of conjugated system of double bonds in a terpenoid, the Diels-Alder reaction is used, which is a general reaction used for the presence of conjugated systems in the natural products. Then comes the number of rings, that how many rings are present in that a particular hydrocarbon or whether it is a acyclic hydrocarbon. Now from the steps which we have discussed, that the molecular formula, the nature of the oxygen, the unsaturation, after these all, the number of double bonds and the nature of functional groups, after discussing all, then the step comes the number of rings. it is possible to find out the molecular formula of a parent saturated hydrocarbon of a terpenoid, which on comparison with the formula as we have shown in the table, it reveals the information about the number of rings present in the terpenoids. If after calculating the molecular formula, if the hydrocarbon formula comes CnH2n plus 2, then the compound would be acyclic. If it comes CnH2n, then the compound will be monocyclic. It means it will contain the one ring. If it comes CnH2n minus 2, it will be bicyclic, and if it comes CnH2n minus 4, it will be tricyclic, and if it comes CnH2n minus 6, it will be tetracyclic. For this we have taken one example. The molecular formula of citral is C10H16O, which contains 2 double bonds and 1 oxygen atom as a carbonyl group. Thus the molecular formula of the parent hydrocarbon would be C10H16O, which is equivalent to C10H16 plus the 4 hydrogens, which are basically because of the 2 double bonds present. And since one carbon oxygen, which is a carbonyl nature, so for the double bond we can add 2 hydrogens. So by adding these again 2 hydrogens, 2 more hydrogens for the carbonyl oxygen equivalents, the molecular formula will then become C10H22. And if we convert this molecular formula into the general formula, it will convert into the CnH2n minus 2. And this is the general formula for the acyclic compounds. So from here we can conclude that the citral must be acyclic in nature. There is no ring in the citral terpenoid. Then comes the oxidative degradation products. After the discussion of the ring, then we will decompose the compound. We will oxidize the terpenoid compounds with the different oxidizing agent, and we will convert this terpenoid into the smaller moieties, and by the structures of the known smaller moieties, then we will back calculate the structure of any terpenoid. Then this method includes the degradation of the terpenoids into the smaller fragments which are of the known structures. Degradation may be carried out by various means, but the most important method is the oxidation method. The common oxidizing agents which are generally employed in the terpenoid chemistry are as follows. One of them is a nitric acid. Sometimes nitric acid is used to effect the oxidative degradation, as there is a very powerful oxidizing agent. It degrades the terpenoids drastically to a mixture of aliphatic and the aromatic acids. For example, camphor, when it is oxidized with nitric acid, it converts into the camphoric acid as well as in the camphoronic acid. Then comes the ozone oxidizing agent. This reagent attacks the olefinic linkage of the molecule to form the ozonide, which upon decomposition either by hydrolysis or by catalytic reduction, it yields the corresponding carbonyl compound. First the ozonide is formed, and then after hydrolysis it will convert into these 2 aldehyde or ketones, which are generally the known compounds, and from here we can design the structure of a particular terpenoid. Here again we have taken the reaction with the ozone, and the products will be aldehyde and ketones, which are generally the known structures, so we can design the structure of the terpenoid. Then comes the sodium hypohalite. This reagent is used for the removal of one carbon atom as a bromoform or the iodoform from the methyl ketone. If we have this methyl ketone linkage in the terpenoid and we will do this kind of reaction, then we will get the 2 side products. One is a bromoform and in the second reaction it will be the iodoform. So we can conclude that the terpenoid will contains this kind of moiety. Then the next oxidizing agent is hydroxylating reagent. Examples of these reagents are acetic acid, peracids, osmium tetraoxide, H2O2 and KMnO4. When these hydroxylating agents like osmium tetraoxide, when it is attacked on this double bond, it will form this kind of complex which upon hydrolysis will give the glycols again these glycols are known structures and we can calculate the structure of the terpenoids. So from these oxidative degradation methods, when we degrade the terpenoid into the smaller moieties which are known structures, we can calculate the structures of the terpenoids. The other methods we will discuss in the second module.
With this note, thank you ma'am, thank you so very much for giving us this productive session on terpenoids. And dear friends, we will be meeting again tomorrow and would be discussing more. Till then, take care, goodbye, and yes, do write to us at info.cec@nic.in if you have any query or feedback. Thank you ma'am, thank you once again.